Now that we've finished with ooginess that is summation notation, we can tackle the definite integral. If I want to find the actual area under this curve, I could add up these a1 through an, but I don't know what they are. We estimate them using our rectangles. Now this is an example of using the right sum, where I've used the right side of the interval to come up with the height of the rectangle. I have broken this up into n pieces, so if I want the right sum, r sub n, I have b1 through bn, adding them up. And using our summation notation, I can write that as I goes from 1 to n of b sub I. Let's break this down. To get the area for any one of these rectangles, I need the base, the size of the base. We call that delta x, for change in x. There are n chunks, and the length of this interval is a to b, so the size of delta x is b minus a over n. What do I need next? I need to come up with the height. Well, to do that, I need to find out what f of xi is. F of x1, 2. I need a generic statement for f of xi. Well, xi, notice x1 is a plus a delta. x2 is a plus 2 delta. x3 is going to be a plus 3 delta. So in general, a sub I is a plus I times delta x. So the actual area is going to be the limit as n goes to infinity of r sub n. Remember I mentioned this a while back. It doesn't matter if I use the right rectangle or the left rectangle or the midpoint rectangle or even the trapezoid. As long as this function is nice and smooth and continuous, any one will work. I'm using the r just to make calculations more easy. So putting it all together, the actual area is going to be the limit as n goes to infinity. The summation as I goes from 1 to n of f of xi delta x. So, and this is known as the Riemann sum because Riemann came up with it. Let's do an example. Now, you and I both know that this area is 12, but we're going to forget that for now. And we're going to pretend we don't know that. So the area is the limit. I just regurgitated the formula. I goes from 1 to n, f of xi, delta x. So in this example, sorry, my cat's being a dick. So in this example, my delta x, I'm going from 0 to 4, so I've got 4 over n. My delta x is 4 divided by n. My xi, which is a plus I times delta x, a is 0, that's sweet. So my xi is 4i over n. Plug that into my function. My function is x plus 1, so my function will be 4i over n plus 1. Put this all together in my formula. I have the limit as n goes to infinity of the summation as I goes from 1 to n of 4i over n plus 1 times 4n. Now we need to give ourselves some more space and go to the next page. We need to simplify this before we can attack it. So I can distribute the summation sign, and the 4 over n can come out because things that don't have an I attached to it can come out because it's the I that's changing. So now I've got 4 over n, summation I go from 1 to 4, 4i over n, plus the summation I goes from 1 to n of 1. Or I can pull 4 over n out because it's just a coefficient and it doesn't have anything to do with the I. The I can't come out, but the n's can. And now I can remember my formulas, which I don't know if that's where you are. Stick this over here. Summation from 1 to n of 1 is n. The summation from 1 to n of I is n times n plus 1 over 2. So I'm going to plug that in and simplify it. And as n goes to infinity, this goes to 12. Recall, if you have a polynomial over a polynomial, and n is going to infinity, you're looking at the leading coefficients. The leading coefficient on the top is 12, and the leading coefficient on the bottom is 1. So I'm getting the limit is 12 over 1, which is 12. I think we said that 2 slides ago, but we worked really hard to get it this way. Let's try a grosser example. Suppose I have 1 plus x cubed and the interval is negative 1 to 1. Okay, the width of my interval is 2, so my delta is 2 over n. My xi is a plus I delta x still, but plugging my formula, this time my a is negative 1. So my xi is negative 1 plus 2i over n, which means my f of xi is 1 plus that gross stuff cubed, which I will simplify off screen and it gives me this. So f of xi is 6i over n minus 12i squared over n squared plus 8i cubed over n cubed. So putting it all together in my summation formula, so I have limit as n goes to infinity, I have f of xi, which is this really gross polynomial thing, delta x is 2 over n. I have to simplify this. So what should I do first? Well, I pulled the 2 over n out, but then also n, then pulled it out and distributed the summation sign. So I have 12 over n squared times I, that's this one. See, I have 2 times the 6, and the n squared is on the outside, but the I is left on the inside. When I put the summation over here, I have a negative. I've got the 12 times the 2, so I've got 24 on the outside, and n cubed also on the outside, and the only thing left is the I cubed. And the last one, we have 16 over n to the 4th times the summation as I goes from 1 to n of I cubed. Now, I have formulas. There are my formulas. I need to plug these formulas in for these summations. And I get that. Now, before we panic and go, holy shit, this is really gross. We're taking the limit as n goes to infinity. We have 3 different terms. I'm going to look at each term separately. If I were to multiply this thing out, the top would be 12 times n squared plus some other crap of lower degree. The bottom is 2n squared. This is 24 times 2n cubed over 6n cubed. This is going to be 16n to the 4th over 4n to the 4th. This is not as bad as we think it is. We don't need to multiply all this crap out. Unless you're a masochist, please don't do that. Know that if you were to multiply it out, this first one would give you 12n squared plus some crap that we don't care about. This next one would give me 24 times 2n cubed plus some crap I don't care about because it's of lower degree. And this would be 16 times n to the 4th, again, plus some crap I don't care about. So using that theorem we had before of leading coefficients, this thing here, this first term, goes to 12 over 2. This goes to 24 over 6. So 24 times 2 over 6. The last one goes to 16 over 4. Simplify, and I get the answer is 2. So, a little tedious, but you need to practice this because I'm going to make you do it on a test and a quiz or something. So, that's the grossest I can make it. Well, it's not, but it's the grossest I will make it for you. Let's look at this one. Suppose I have A as the area under this curve, and this curve is defined by e to the negative x, and I want the area between 0 and 2. Well, let's see, my delta x is going to be 2 over n. I have my function values are going to be e to the xi. So if I wrote it as a summation, I would get this. I can't do this. I cannot do this right now. I don't have any formulas with e. The only way we can do this one is to estimate it. We can make n bigger and bigger and bigger, but I don't have any cutesy formulas for this. So we're not going to look at it. We're not going to play with it. Goodbye, baby. Something to keep in mind, this formula, the limit as n goes to infinity, of the summation xi goes from 1 to n of f of xi delta x, is only going to be the area if my f of x is positive. If my f of x dips below, then I'm going to get negative area because the height of the rectangle would be negative. So if the stuff on top is positive and the stuff on bottom is negative, and it'll subtract off if you integrate it. For right now, we're just dealing with area. We're just going to call it area. I've done this entire slideshow without saying the name of the title of the show until now. This is known as the definite integral of f of x from a to b, this limit. Regardless of whether f is positive or negative, the integral is this limit, would give us the area if it was all positive, it would give us some summation of positive and negative if it flopped above and below the axis. Practice doing a couple of those really nasty summations. Yes, I know some of you have taken calculus and know the shortcut. Don't use it. Well, you can, but you won't be able to use it on a test, and I'll get really mad and cross at you because I had to go through all this shit, so you have to go through all this shit. It will make you stronger, trust me. That's all for now. I'll see you in the next video.